So I resume recording. Good morning, everyone. So we should finish today our clustering objectives. I rapidly explained last time how it works, but apparently, indeed, it's not enough. There was not enough time for cover this topic, so I will repeat it in more details now, and we'll see how it works, how it's implemented. This spectral clustering is implemented in MATLAB in the standard package for image processing. So the clustering objective, the idea is that inside the cluster, the weight inside the cluster, weight of connections, information, should be more, more intensive than outside the cluster. So elements within a cluster should be closer, similar, more similar to each other than outside the cluster. So people within the same group are similar, more similar than with outsiders. Okay, so this is the general principle, and this we could use. So the major message for today is that we can spare our time and efforts not performing the pairwise comparison between different, say, items or individuals or within a group. Okay, we can use linear algebra. And the second eigenvector, second eigenvalue of a particular operators, self-adjoint elliptical operators defined on our database would help us with that. So this is my main message for today. Okay, so that's what I already shown you, that we simply, okay, so suppose we have a set of, a group of 6 individuals, and we need to perform clustering. We analyze somehow similarity between them. So similarity in the graph theoretic model of data, similarity is a kind of weight on the edges. And then there is something in between these two groups. Okay, so indeed, I just wrote these numbers, from head. I mean, it's not a real data. It's just a toy example. Okay, so the idea is very natural. I need to minimize. I need to find a procedure which automatically detect me the optimal cut. Optimal cuttings is such that the sum of weights of edges I'm going to cut should be minimal of anything. Okay, for my case, it's obvious, right? Because I constructed 2 triangles, assigned high weights, strong weights within triangles, and some small weights in between them. Okay, but just to show you how it works. So, well, cut means that we just sum the weights. Okay, the weights of edges we want to cut. Well, these cut edges should have one end at one group, another end at another group. Well, yes, so in our case, everything is obvious. My cut, suppose, which I'm going to search for, is 0.3. Okay, indeed 0.3 is less than any weight within each group, so I'm secure. Okay, first message, first idea, important idea here. Indeed, you might get different weights. You might get completely, yes, something goes wrong. I got message. Are you changing slides? I'm not being able to see. Yes, I'm changing slides. I can stop share and then resume. Okay, so yes, I stop sharing and then now I resume. Do you see me? Okay, so these are okay. Yes, yes. Thank you. Thank you so much. Now it's good. Okay, perfect. Well, yes, so I'm searching for minimal cut. Cut is the sum of weights of edges in between two groups. One end of an edge belongs to group A, say, another end of an edge belongs to group B. And I need automatically be capable of finding some set of edges which connect my potential candidates for groups, and the sum of all weights should be minimum. So it's a cut minimization problem. In my case, in my toy example, cut is 0.1 plus 0.2 is just 0.3, and it definitely less than any weight within a group, within these triangles. That is my toy example, just to be obvious. I mean, that my example should be obvious, right? Now, normalized cut, so that's what I wanted to explain. In my case, you see that everything was obvious, and my weights were small enough because I have chosen them in such way. In reality, edges might respect some relations depending upon the unit of measurements, billions of dollars in contrast to thousands of dollars, okay? You see that numbers might be huge and incomparable. In one group, I might get billions on edges. On the other group, in the other group, I might have thousands. Okay, so clearly, if I would take the weights as they are, when I perform all these calculations on a computer, moreover, computer might make some rounding errors and so on, I might get trouble. Well, it might either take too long to compute or I might get troubles. So people usually use the normalized cut criteria. So they take the cut between A and B, in my case is 0.3, and divide it by the volume of A. Volume of A, it's the sum of all weights within a group A, within a triangle A. 0.8, 0.6, 0.7, okay? And they add also, to make the problem symmetric, symmetricity plays the important role because we will see, because it's just a requirement from linear algebra. Why, I will show you later. And we sum it with the cut from AB divided by volume B. Now it's well balanced. Even if I had billions in one group and thousands in another group, now everything is more or less balanced. It's just symmetric weight. So I'm searching for optimization or minimization of this function instead of simply observing these quantities. Why? Because if there are just two edges I'm going to cut, and I can just check it by by hand basically here, right? So I'm here, I'm safe. But if I have thousands of connections and billions of nodes, it would not work. I wouldn't be able to find all possible cuts here. Well, so volume is the total weight of the edges originating from the group A. Okay, so again, so this normalization criteria is just for be secure, for get a balanced partition, because if it's biased partition, definitely billions, the group with billions would get some preference, might get some preference, okay? Now, yes, so we are not going to check all weights, even on computer. We are going to perform algebraic procedure because it's much more cheaper and faster, okay? So first step, we calculate, so we have our weight matrix. We are able to calculate, weights are all non-negative, right? They might be zero if there is no connection, but they are positive if there is. Okay, we can calculate eigenvalues and eigenvectors of this matrix. Weight matrix might not be symmetric, okay? So, and then we have the first problem. If I calculate eigenvectors and eigenvalues of this matrix, of non-symmetric matrix, I might get complex conjugated eigenvalues and complex eigenvectors. It's a great headache. Why? Because usually I want to have a real Cartesian space in which I should have points for my quantities. And then those points which are close to each other might be clustered together. Those which are far, not of the same mold, I just think that they belong to separate clusters. You see, it's always some kind of geometric mindset on the background. So I'm going to avoid all possible non-symmetric contributions because they give me complex values in the eigenvectors and in the eigenvalues. Well, I don't want to work with this complexity. I should go to symmetric forms of whatever I do. I should go finally to symmetric operators. So the idea is that, okay, so first use the idea of spectral graph theory. We can analyze the spectrum of matrix represented by a graph. Again, we constructed a graph from this data, from the relational database. We calculate the eigenvectors, eigenvalues. First step. Now, okay, first idea, use simply matrix of weights. And if I consider, since, you know, I don't have directions in my edges, I can say that I have an undirected graph. It's a little bit of simplification. So I have weights, and I can construct a symmetric matrix here. So my graph is simple. There is no self loops. Weights on the major diagonal are 0. Out of the major diagonal, I have my weights. So I have symmetric matrix. I have eigenvalues, which are real, because matrix is symmetric. All values are non-negative. And eigenvector forms the orthonormal base. So in principle, if I calculate these eigenvectors, I can use them, some of them, as a coordinate frame for mapping all my other, you know, all elements in some geometric space. So it's called algebraic embedding. Now, but this is one possibility, right? Okay, so one matrix, adjacent symmetrics. Okay, it works because my example was trivial. Moreover, you see that here my weights were less than 1, all of them. But in reality, if I'm really take a real data, there might be any numbers. So I feel myself insecure again, from the point of view of computation, from the point of view of biases and so on. So I should perform next step. Next step is to go to, well, I will skip these few slides to return to them back in a second. And I explain the major philosophy. Instead of working with adjacency matrices or affinity matrices, what we explained before, people prefer to work with Laplace operators. In general, if you are not able to construct a Laplace operator, we will discuss how to construct it in a minute. Actually, last time I already mentioned it. If we are not able to construct a Laplace operator, please construct any elliptic self-adjoint operator. Elliptic operator, elliptic equation, elliptic differential equation, it's a diffusion equation. The leading coefficients in the diffusion equation should be positive, which means that there is no particular direction. There is no bias. Imagine a diffusion. So I have a graph, or I mean, just, you know, random walkers which move from node to node, or if I think about a relational database, from entity to entity, following weights defined by the relational database. So I have a diffusion process. Why I like diffusions? Because diffusion has no particular direction. It's not biased. It goes simultaneously and with equal rights to any direction. I don't have any bias in my apprehension of this database. I just follow symmetries of weights or patterns which might be, you know, encoded there. If I use some non-elliptic operator, it apparently corresponds to some biased random walk or anisotropic random walk, and some directions would be preferable. It means that with high probability, I would choose some particular entities within my database. It means that then these pre-chosen, I mean, preferred groups of nodes would give me some strange results. Okay, so I'm trying to be unbiased, equal, fair, with respect to all possible directions. So people use diffusion processes, and for diffusion process, they formulate the they construct the Laplace operator. The first step of constructing the Laplace operator is to construct a degree matrix D. So I had initially my matrix A, right, of weights. On the major diagonal, I had zeros. Now I sum all my weights. So it was my matrix A. I sum all my weights attached to x1, all weights attached to x2, all weights attached to x3, and so on. This is my degree matrix. It is a diagonal matrix with a sum of weights attached to a particular given node on the major diagonal and zero otherwise. Then second step, so then I take construct the Laplace operator like that. So it's just a degree matrix minus A. Okay, since D is a sum of all rows in A, it means that there should be a zero eigenvalue. And the minimum eigenvalue, so in fact, I inverted the situation, right? So if I consider spectral properties of A, I would get some, I mean, since all elements in A were non-negative, I get some big number as the major eigenvalue, and then smaller numbers, you know, as other eigenvalues. Now, my major eigenvalue, which corresponds to Perron-Frobenius eigenvectors. You remember the eigenvectors with no zeros, they are signed definite, either positive or negative. This Perron-Frobenius eigenvector corresponds to the major eigenvalue of Laplace operator, and the major eigenvalue is zero. It's not one like for random walks. It's not, you know, the degree of the node, average degree of the node for a normal graph if I use the adjacency matrix. It's always zero. So my major eigenvector is zero, which express the idea that in diffusion, the amount of these random walkers, number of these random walkers should be preserved. There is no any sink nor source. Okay, so this is the diffusion process. I construct this. Now I have a symmetric matrix. On the diagonal, I have some big numbers. Out of the diagonal, I have 0 or negative numbers. A little bit, well, this might be small, right? Now, properties of the Laplace operator. Eigenvalues are non-negative real numbers. Non-negative means that the minimum eigenvalue is 0, all others, it's always simple. It's just Perron-Frobenius theorem turned upside down. And my eigenvectors are real and orthogonal. Again, I can use them as a basis for mapping, for algebraic mapping. Yes, okay. Fan Chung. So she coined the normalized Laplace operator. My initial Laplace operator is d minus a here, and she just proposed to multiply it from the left and from the right by the 1 over also other the diagonal matrices. On the left and on the right, on the major diagonal, I have the same degrees, the sums, but square root 1 over square root of them. What does it give it to me? It gives me 1 on the major diagonal. Always 1. Why is it important? It's important for computers. Calculation, I mean, contemporary, I mean, nowadays we have algorithms for algebraic computations which are implemented in computers, which give enormous advantage to the matrices which have 1 on the major diagonal. The properties are the same. Eigenvectors are real, normalized. All eigenvalues are non-negative. Everything is perfect. It's just the same story. Yes, the system of you see that with respect to the original Laplace operator, I simply perform some kind of rotation. Since, but for me, you know, I didn't know the properties and the meaning of my orthogonal basis, which I was going to use for algebraic mapping of all my data. I didn't know the meaning of these x's before. I rotated. I do not know them now, but I don't care. The only thing I care is that the resulting frame of reference is Cartesian, orthogonal, normalized. Fine, I'm happy with that. Okay, so now bipartition. So we should find a solution for the problem. So we have kind of an indicator vector pi for all xi belonging to group A, the first group. It should be positive for all xj or xi belonging to another group. My indicator should be negative. Okay, so I'm searching for a solution like that. And I told you already last time that mentioned that this is called Fiedler vector, and this in this normalized system, in this basically in this self-adjoint, it means self-adjoint means symmetric in terms of metrics. Okay, and well, orthogonal system of eigenvectors, I simply have I should choose the second eigenvector. Okay, so it appears that what I'm going to search, in fact, it's minimum. This is my new criteria. It's a transposed vector p of +1 or negative or -1 times L, my Laplace operator, times p, and this is my object of study. Okay. Laplacian is semi-positive, so I have the major eigenvalue 0. All others are greater or equal. Lambda 1 is, or lambda 2, sorry. There should be lambda 2 indeed. Sorry, I'm just, well, it's a little bit, well, it's positive, and there is a gap between 0 and lambda 2. Now, accordingly, the so-called Rayleigh theorem, the minimum value for eigenvalues, the minimum value of these minimization normalized cut problem is given by the second smallest eigenvalue of the Laplace operator. So the corresponding eigenvector is called a Fiedler vector. And I told you that there is very clear intuition beyond such solution. If I take the first eigenvector of the Laplace operator corresponding to the major eigenvalue 0, I have some positive vector. It's a Perron-Frobenius eigenvector. And then my second Fiedler vector should be orthogonal to V1, to this all positive vector. It could happen. So if I calculate a scalar product, I should have 0 at the end. It might happen only if the elements of the second Fiedler eigenvector roughly split in two subsets. One subset is totally positive, another subset is totally negative. And there might be some 0 in between, a node of my vector, of my eigenvector. If I mark graphs with respect to sign of components of the Fiedler eigenvector, second eigenvector, they are either positive or negative or 0. They perfectly characterize the structure of graphs in a natural way. In a natural way means that positive nodes are adjacent to each other. Negative nodes are adjacent to each other. 0 nodes, if they happen, they might be, there might be no 0 elements, but if they happen, they are somewhere in between positive and negative part of the graph. I would not assign any profound meaning to positive and negative components. Okay? It simply gives you an idea. There is one part of the graph, there is another part of the graph. And typically, a customer or a user should define which part he or she is interested in. Okay, so we will see it, how it works in MATLAB. Basically, you should define what is a background and the foreground, and what is a foreground. Nobody else could do it. Okay, now, as I told you that this is there is a current nodal theorem which actually lays beyond this result. It tells us that if I consider the case eigenvector of an elliptic operator, self-adjoint, self-adjoint elliptic operator, if I take the case eigenvector or eigenfunction, if I'm thinking about continuous case, then I should have at least k nodal domains. So if I consider the first eigenvector, Perron-Frobenius eigenvector, it is sign definite, positive, negative, but every element has a positive sign, okay? I have a single, all nodes are packed together into a single domain, positive domain. If I take the second Fiedler vector, then I have two domains, positive and negative. So Fiedler vector is a natural tool for bisection of graphs. It's a natural tool for bisection of databases. In principle, that's all we need, because we can bisect a database or a graph and then take separately each component and bisect them again and again and again and so on. By doing that, we have 2 in power of n different substructures within a graph or within a network. And it works everywhere. You could take any matrix. It might be a relational database, it might be a bitmap of an image, whatever you want. So that's what we actually will work on. Yes, in if, but other eigenvectors. Okay, so this is the formulation of current nodal domain theorem. So we should have an elliptic operator, self-adjoint elliptic operator, which describes, so it's a very wise words, but in fact, well, for a physicist, it means that we define a diffusion process. Why do we need to define a diffusion process? Because it's unbiased. It's isotropic. It goes to all directions simultaneously, and we take all information from all parts. If we use a non-elliptic operator, it has a bias, it has some direction, it has some preference of movement. So we collect information from one direction, we forget about all other directions. Okay, so the idea is very simple, clear here, beyond all these mathematics. Well, then we have, whenever we take an nth eigenfunction, it works also for continuous, differential equations. If you need to, you probably know all these. There are clips in YouTube or very popular. A drum. Okay, you have some dust or sand on a drum, and then you start to beat it, and then it has some harmonics. At different frequencies, you might have some harmonics. There might be some concentration regions, and in some regions there are no sand. That is the current nodal theorem. In some places you have positive islands. In other places you have negative islands. In a sense that there are no sand. That is what I'm going to what I'm talking about. And this is precisely the mechanism how to not even bisect but multisect, how to split the domain into parts, how to split graphs into parts. But the problem is that with higher order eigenfunctions and eigenvectors, that the remaining islands appear to be not well connected. I might have some elements in one part of my drum and some other, sand in some other part. And if I map it into a graph, I might have some red nodes somewhere and blue nodes in other places. They might have meaning, but it's very difficult to explain to a customer. You see, it's not a science in a sense that it always tries to fit expectations from people. Okay, so it should be easily interpretable. Otherwise, it's not saleable. Okay, now just simply, to concluding all this story. Yes, concluding all this story. So pre-processing. So first, please build a Laplacian matrix. You can just construct a Laplacian matrix like that without normalization. If you have a big matrix, use normalization because it gains, you would gain so much from that in terms of calculations, in terms of, calculate the singular vector, singular values of the table. Take the second, you see the smallest eigenvalue would be 0 if you construct the proper Laplace operator. Second is non-zero, the first non-zero, non-trivial eigenvalue. Take the correspondent eigenvector, a column of matrix of eigenvectors, and then map the signs of components to the nodes. So this is the receipt. I mean, not receipt, but scenario, how you should proceed with that. Okay, so for instance, in my case, which I put forward at the beginning of my talk, I have for 3 elements, I have negative components. For other 3, I have positive components that actually immediately gives me the bisection. And this bisection is obviously fits my need because I assign weights 0.1 and 0.2, small weights to these 2 connections. Indeed, it's a toy example, but nevertheless, you see that in this toy example it works, and in principle it works all the time. So you might now, okay, so you might perform this operation many times. You have splitted the graph in 2, then you split subgraph in 2, then subgraph in 2, and so on and so on. That is how the most reliable image recognition techniques works. You probably know that nowadays everyone in this machine learning business are talking about deep learning, neural networks, long short time memory networks, recurrent networks, shallow neural networks. We will discuss it in due time. But if you try to open your mouth and pronounce these words to a guy from Department of Defense, to a guy from Homeland Security, real people, okay, to medicine, to health department, they would just throw you away because it's just a media soap bulb, all these neural networks. Nobody understands how they work. Their results, one day you would get a perfect classification and you would publish a paper. Another day you perform the same, you take the same neural network, you perform the same analysis, you get completely different results. It's not robust. In the serious business, people don't use them. They use this thing, bisections, trisections. Depends upon the problem you are going to work with. But that is how they are doing. They consider a picture. They first define a foreground, background. That's we will do, I guess we should do it today, certainly. Then they perform another bisection in the background. They find sky and water and land. Then in land they have trees, shore. Here in the foreground they might have mermaid, rocks, and so on and so on and so on and so on. So sequentially, performing sequential bisection, you would get all, you would recover all layers within your image. Okay, so that is right. So in principle, people try to use higher order nodal domains. There is a hierarchy of nodal domains because basically you remember that I take a fiddler vector, I have a bisection. If I take the third vector, I have affine structures within my bisections, and so on and so on. Okay, in principle, it's possible to perform a classification of elements. So for instance, I take the very first eigenvector, I have a horse, I perform a bisection, I have some segmentation, then the segmentation become finer and finer. So this is the scenario how it works, and that is what in most of reliable applications, so not all military applications, all this artificial intelligence in military means that they simply analyze the domain of elliptic self-adjoint operators defined in a particular databases or images. No room for neural networks. Even shallow neural network are just, support vector machine. That is the only thing they accept or they agree to consider. Okay, we will. It's In due time, we will discuss it. Now, spectral clustering by, okay, so now, there is another method, quite efficient without constructing a singular value, without constructing a Laplace operator, but simply use the singular value composition. In fact, you have, you remember that singular vectors, values and singular vectors, these are eigenvalues and eigenvectors of quadratic matrices, of matrix of multiplied by its transpose in two ways, and then you have say two groups of, so it's in fact it's just they are non-negative. You could consider them as adjacency matrices of a graph or affinity matrices, some weights, okay? And then you could simply apply the singular value decomposition. Take the major eigen, so you have, for instance, an adjacency matrix of the graph. You calculate the major singular vectors. And then in this, if you just look at this singular value vectors of any more or less normal matrix or rectangular table, you would get the same phenomenon like we observe in elliptic self-adjoint operators with current nodal domain theorem. So the higher the eigenvector, singular vector, the more domain it would generate. In particular, so the first one is everything positive. The second is one part positive, another part negative. Third is three nodal nodes, right, within this graph. So I have positive, negative, positive, and so on, and so on, and so on, and so on. So in principle, it works in the same way. For instance, I can take the first three major singular values, singular vectors, and map my points, my nodes of a graph into, accordingly, the coordinates, elements of these singular vectors. And then I get a picture like that. So the first one gives me just 3 points, and then finally I map all nodes here, and then I would get some clusters. After that, as soon as I get set of points with a well-defined coordinate system, Cartesian coordinate system, I have Euclidean distances between points, and I can use whatever I want for clustering, for instance, k-means or any other, or support vector machine, or any other mechanism or method we will discuss later, how to perform aggregation. Why there are many methods? Well, because different methods work with different efficiency at on different data sets. It's an art, it's not a science. This method doesn't work, which we should check another one. When you open your MATLAB and try to upload your data and choose applications, and for instance, classification learner, it would, you should press all, and then it check all available, say, couple of dozens of methods. You should find the best one for your particular questions, which you now the very last idea is that the same method by using singular value decomposition could be used also for analysis of clustering of abstract data. If I have a data matrix, I can take a centroid to make my analysis balanced, calculate variances. So it's just a vectors in which each column is a departure of a particular value from my centroid, calculate FFT, so covariance matrix, which is which is semi-definite, so it has no negative eigenvalues, and then I completely set with a singular value decomposition. Okay, so I have some singular or eigenvalues in my case, and I can consider, if I like to, for instance, to reduce the dimensionality, at this time I should cut my number of vectors to, say, some k or 2 or 3 or 4, how much I don't know, but it depends upon what I'm going to consider. And then I can construct a projection onto a low dimensional subspace. Okay, And it also performs me clustering. And the clustering is natural because initially I had a lot of points in a multidimensional space. And now I grab them into 2 dimensions or 3 dimensions. I would, I would get clusters, guys, by default. No classification are possible. Classification is a consequence of our narrow-mindedness. Because we are able to, we want to consider everything in 2 or 3 dimensions, therefore we would have clusters. No clusters in reality. It's all clustering is artificial. That's what I wanted to show for the moment, but it's not the end. It's not the end because I want you to open the image bisection MATLAB program. I'm just pressing the MATLAB file. It's very simple and easy. Okay, so now I start sharing screen again. Yes, perfect. So this is my image bisection file, image bisection file. So I just wanted to show you this application. Well, what did I do? I simply no, it's not. Sorry, I should do it other way around. I should use plots. Sorry, I should take it away. Why it does not? I want to show you the picture. I want to show you the picture of a baby. Why images? Okay. Well. Okay. Let's do the following. I open applications. In the applications, I have image processing, signal processing, communication, control, image processing and computer vision, image segmenter. So this image segmenter uses the fiddler vector of a picture. Okay, load image from workspace. Excellent. Okay. Yes, so this is a picture. Okay. What can I do? Okay, so I perform a graph cut. Yes. Now, I should mark what is foreground, what is background. The bitmap is already calculated, so the second this fiddler eigenvector is already done. Okay, it's already known. Now I should choose which part I consider positive as foreground and negative as background. So I consider foreground here and background here. Okay, that is a bisection. Then I can take, yes, I don't see, show binary. Okay, create mask. Create mask. Okay, so first of all, indeed, it's possible to show binary to make it black and white. I can create mask and then use this mask for other pictures and so on and so on. Okay, that's what I wanted to show you. Another small feature. What's going on if I take a picture like that with the fog? I try to perform a graph cut. I say, okay, so okay, sorry, no, erase. I don't want. I think foreground is here, background is there. Okay, you see, in principle, in some cases, it's not quite clear where our understanding of an image might not coincide with fiddler vector. That is what I wanted to say, guys. Maybe it's not that quite clear, but nevertheless, okay? Whenever you, because your mind considers some objects, Okay, but if there is a fog or whatever else, Fiedler eigenvector might not follow your ideas of your mind, interpreting the picture. And this is a very subtle and important moment. Your customers and yourself might confuse. Your methods might give you something which is not perfectly fit the expectation. Thank you so much, guys. Well, I stop sharing and will stop recording.